Good day, everyone. In this lecture, we'll be considering block codes, which happen to be a form of error correcting codes. Now, the primary objective of the communication design is to realize the required data rate within the bandwidth constraints of the available channel and power constraints of the particular application. So, this data rate must be achieved within an acceptable bit error rate and time delay for good quality of service. In practice, to achieve the required bit error rate, error control coding is required. And error control coding is used to detect and in most cases correct symbols that are received in error. So error detection can be used as the initial step before error correction, like the automatic repeat request, which uses redundancy for error detection, after which it triggers the receiver to request a repeat transmission of the corrupted code word through a return part of the duplex link, such as more like the three-way handshake, where an acknowledgement is sent, either a negative or a positive acknowledgement. And another technique is the forward error correction, which relies on controlled use of redundancy in the transmitted code word for both the detection and correction of errors on transmission over a noisy channel without the need for any retransmission. So basically, error correcting codes are classified into block codes and convolution codes. And in this lecture series, or in this lecture, we'll be talking about the block codes. Now, in comparison with the convolution codes, block codes do not require memory in the encoder, while the convolution codes are classified by the presence of memory in its encoder, that is, the use of shift registers. And now let us consider an NK block code capable of detecting and correcting errors, okay? Over a noisy channel. So the NK block code comprises of an information in successive k bits blocks, for which is added an NK redundant bits that are algebraically related to the k message bit, thereby producing an encoded block of n bits. So we have n as the encoded block of bits, or the encoded bit, that way. Bits by k happen to be message bits. So the n bit block is called the code word, such that we have, this is the encoded dot. So this is n, that's the block length. Okay, just the block length. And here we have message bits. Okay, so and here we have the redundant bits, and the block length minus the message bits minus k. And what we have here is the code word. So hence the code word is a combination of the message bits and the redundant bits. And this is what is transmitted by the channel. In order to move on in this lecture, let us describe a few terminologies. The code word. Like I mentioned earlier, we have the block length n, we have the message bits k, we have the redundant bit n minus k. I'll say this is the code word, right? So the code word is the encoded block of n bits. So it contains the message bits, okay, and redundant bits. Or better still, parity bits, n minus k. Okay, and then we have block length n, which is the number of bits n after coding. We have the code rate, and this is the ratio the message bits, message bit k, encoder output, bit n. It is given as r, which is the same as the message bit over the encoder output. For 0, there's an r, there's an 1. And then we have the channel data rate. This is bit rate and the output encoder. So if the bit rate at the input of the encoder is r sub x, then the channel data rate will be the same as n over k rs. That's if This is the rate at the input, then the output data rate will be R naught. Then we have code efficiency. And this is the ratio of the message bits in a block to the transmitted bits for that block by the encoder. So code efficiency here, we have message bits in a block over transmitted bits for the block. Okay. Now, for an NK block code, there are K message bits, and then N transmitted bits, which is the code word, so that the code efficiency is the same as K over N. You see, this is the same as the code rate. So, systematic code. This is a code in which the message bits say K are explicitly transmitted, together with the parity bits. N minus K, such that we have the block code. This is a block, better say the block coder. Then we send in the message bits, is K. Then we get the coded bits, that is N, such that the rates are the same as K over N, such that what we now have will be the message bit, clear distinction between the message bits K and the parity bits. So that here we have K, then here we have N minus K, we have N. So this is an NK systematic block code. Inversely, we have a non-systematic code. It's a code in which the N bits code word may not contain any of the information bits explicitly. Let's consider linear block codes. Now, a code is said to be linear. So the code is linear if the sum of any two code words produces another. So this property of linear block codes is called closure. Okay. So let us consider message bits, given message bits m, taking on values m0, m1, all the way to mk minus 1, and then parity bits b, for instance, taking on values from b0, b1, all the way to bn minus k minus 1. So these are message bits. These are parity bits. Now, if the code vector C is given as C0, C1, all the way to Cn minus 1, the code vector, then we have the relationship C being the same as B M. So that the code word is a combination of the parity bit and the message bit. But the parity bit, we have that the code word is a combination of the parity bit and the message bit. But the parity bit B can be written in the compact matrix form, where P is the n by n minus k coefficient matrix. And it is defined by P is the same as P00, P10, all the way to PK 10, P01, P11, all the way to PK minus 1, 1. You will have all of this, then P naught n minus k minus 1, and P1 n minus k minus 1, the way to Pk minus 1, n minus k minus 1, where the Pi sub j is either 0 or 1. Right? So if we substitute for this property, then we have that C is the same as M parity times the identity matrix, where I sub k is the identity matrix, k by k matrix. So that gives us I sub k, which is the same as 1, 0, 0, 0, 0. This is 1, 0, this 0, 0, 0, 0. But the K by N generator matrix is given by G, or the parity times the identity matrix, such that C will now be the same as the message bit times the generator matrix. Hence, the full set of code words referred to simply as the code is generated in accordance with this expression. Okay? Hence, the generator matrix is used for the generation of code words. Alternatively, the relationship on the parity check bits will be given as H is the same as I n minus k transpose of the parity, where P transpose is the transpose of the coefficient matrix, P, and In minus K is the corresponding identity matrix, the corresponding identity matrix. Hence, the parity check matrix times the transpose of the generator matrix is the same as the generator matrix times the transpose of the parity check matrix, and this will be equal to 0. And the generator and the transpose of the generator matrix and the parity check matrix here are used for further analysis or estimation, in that the parity check matrix is used for syndrome decoding to check for errors. At the receiver, while the generator matrix is used for generation of code words at the transmitter. Hence, the code word times the transpose of the parity check matrix is the same as the message bit times the generator matrix times the transpose of the parity check matrix will be equal to 0. Okay. Hence, we have that the generator matrix, for instance, generator matrix G takes in the message vector M and then gives an output of the code vector C. Why the parity check matrix, H takes in the code vector C, and then generates a null vector 0. And should it generate a null vector 0, then the implication is that there is no error in transmission. So while this operation is performed at the transmitter, this function is performed at the receiver. Let us consider single parity check codes. This is a type of linear block code with the capability of detecting single error by adding a single parity check bit to the data sequence. And it can either be even parity or odd parity. Depending on the number of ones after adding the parity check bit. So if we consider a sequence, say 1 0 1 0 1 0 0, since the data sequence contains 3 ones, the addition of another 1 will result in an even parity. So should we now add 1 0 1 0 1 0 0 1? So the fact that we have 4 ones makes it even parity. Now, should we add a 0 1 0 1 0 1 0 0 0, then the fact that we have 3 ones makes it odd parity. Then we have repetition code. Now, this is the simplest type of linear block codes, which allows the transmission of single message bits n times for the purpose of error correction. Hence, a single message bit is encoded into a block of n identical bits, producing an n by L block length or block code. This block code allows provision for a variable amount of redundancy. The only 2 code words in the code are all an all 0 code word and an all 1 code word. Okay. Let's consider minimum distance requirement. Given a pair of code vectors, say C sub I and C sub j, that have the same number of elements, then the Hamming distance that is D Ci Cj between the 2 code vectors is the same as the number of elements in which they differ. And then the Hamming weight WC of the code vector is the number of non-zero elements in the transmitted code vectors. Okay, so that's the number of non-zero elements, that is the number of ones in the transmitted code vector. So let's assume we have a code word equal to 11011101, and the weight will be 1, 2, 3, 4, 5. We have 5 ones. So the Hamming weight will be the number of non-zero elements in the code word, which is 5. Now we also have the minimum distance, dmin, of the linear block code. It is the smallest Hamming distance between any pair of code vectors in the code. This is the smallest distance between any pair of code vectors in the code. It is the same as the smallest Hamming weight of the difference between any pair of code vectors. Now, the minimum distance of a linear block code is an important parameter of the code since it determines the error correcting capability of the code. So the minimum distance determines the error correcting capability of the code. Hence, an NK block code can correct all error patterns of weight T or less if and only if the Hamming distance is greater or equal to 2T plus 1 for all Ci and Cj. However, the smallest distance between any pair of code vectors in a code is the minimum distance of the code, that is dmin. Therefore, for an NK linear block code of minimum distance, dmin can correct up to T errors if and only if T is less than or equal to half of the minimum Hamming distance minus 1. So let us look at a class of code, the Hamming code or codes. Following directly from the previous discourse, now Hamming codes form a part of the family of NK block codes that have the following properties. We have the block length to be n equal to 2 to the power of n minus 1. Now we have the number of message bits to be k equal to 2 to the power of n minus 1. And then we have the number of parity bits, which is n minus k, which is equal to n, where m is greater or equal to 3. The Hamming code codes a single error correcting perfect code, single error something perfect codes. So cyclic codes. Cyclic codes form another subclass of linear block codes, and the code is said to be cyclic if the following properties are satisfied. 1. The linearity property. Such that the sum of any two code words in a code is also a code word. Okay? The sum and two code words is also a code word. Then we have the cyclic property. Cyclic property that any cyclic shift of a code word in a code is also a code word. So any cyclic shift of a code word in a code is also a code word. So cyclic codes are therefore lateral. They are either lateral or cyclical shift of one another, and can be represented and derived using polynomials. Okay? All the code words of a cyclic code are multiple of some polynomial g of x modulo xn plus 1, such that g of x divides xn plus 1, g of s divides xn plus 1, where g of s is called the generator polynomial. So let's consider some advantages of cyclic codes. The error correcting and decoding methods of cyclic codes are simpler and easier to implement. So these methods eliminate the storage needed for lookup tables decoding. Okay? Therefore, the codes become powerful and efficient. Also, the encoders and decoders for cyclic codes are simpler compared to non-cyclic codes. The cyclic codes also detect error burst that spans many successive bits. Cyclic codes also have a well-defined mathematical structure that permits higher order correcting codes. Hence, very efficient decoding schemes are possible with cyclic codes. Cyclic codes also have easy syndrome. And cyclic codes provide standardization like cyclic redundancy code 8th or cyclic redundancy code 32 and so on. But the fundamental disadvantage of cyclic codes is that the error correction is a little complicated since the combinational logic circuits in the error detector are complex. Okay, so let us consider cyclic redundancy code, check code, cyclic redundancy check code. These are cyclic codes well suited for error detection. Okay, the cyclic codes well suited for error detection. The binary NK cyclic redundancy check code are capable of detecting the following error patterns. Okay, detecting the following error patterns. One, error burst of length n minus k or less. Also, a fraction of error burst of length n minus k plus 1. The fraction equals 1 minus 2 to the power of minus n minus k minus 1. And also, a fraction of error burst of length greater than n minus k plus 1, and the fraction equals 1 minus 2 minus n minus k minus 1, and also all combinations of d mean minus 1 or fewer errors, and then all error patterns with an odd number of errors if the generator polynomial g of s for the code has an even number of non-zero coefficients. So an example of cyclic redundancy check code is the CRC ITU code with the generator polynomial. That's the generator polynomial g of x equal to 1 plus x to the power 5 plus x to the power 12 plus x to the power 16, and n minus k, the redundancy, is 16. Another class of linear block codes is the Bose, Chaudhuri, Hocquenghem. That's BCH codes. Now, these codes are characterized by the block length n equal to 2 to the power of n minus 1, then number of message bits as k being greater or equal to n minus mt, and minimum distance of d mean greater or equal to 2t plus 1. And for any integer, m and t, m is greater or equal to 3, and t is less than 2 to the power of n minus 1 or 2. Now, each BCH code is a T error correcting code. So BCH codes are T error correcting codes. That is, it can detect and correct up to T random errors per code word, where T is the maximum number of detectable errors. BCH codes are cyclic codes. Okay? And also, we have the read Solomon codes. They are referred to as the ROS codes. Now, Solomon codes are an important class of non-binary BCH code. Okay? Let me tell us non-binary BCH codes. The encoder for an ROS code differs from the binary encoder in that it operates on multiple bits rather than individual bits. Okay? So a T error correcting Reed-Solomon code has the following properties. Block length n equal to 2 to the power of n minus 1. Symbols. Then we have the message size of k symbols. Then we have the parity check size of n minus k equal to 2t symbols. And then the minimum distance d mean equal to 2t plus 1 symbol. So given a 7x4 cyclic code with generator matrix to 1 plus x cubed, determine 1, the code word if the message bit or data word is 1011, and 2, the data word if the code word is 110010. So in this case, we represent the data word in the equation form such that D is the same as 1011. such that d of x will be, this will be d naught or s naught. Let's put it out to s naught. S naught, S1, S2, S3, which would be the same as 1, x squared, x cubed. Hence, d of x will be the same as 1 plus x. Now, x is 0, so we knock that off. Then we have x squared plus s cubed. So the x to the power of 1 is turned off. Now, we know that the code word is given as the message bit times the generator matrix. So M will be the same as d of x, which is the message bit or data word, right? Such that G is the same as g of x, generator matrix given, so that the code word will be the same as d of x, g of x, which is the same as 1 plus x squared plus x cubed times 1 plus x plus x cubed. And once we expand this, we get 1 plus x cubed plus x squared plus x cubed plus s to the power 5 plus s to the power 3 plus s to the power 4 plus s to the power 6. That will be 1 plus x squared plus x cubed plus x cubed plus x cubed plus x to the power 4 plus s to the power 5 plus s to the power 6. Now we call modulo 2 addition. So all of these are modulo 2 addition. Okay. So all modulo 2 addition. Such that for this, one plus one is 1, is 1 plus 1 is 0, plus 1 is 1. Okay. Then we now have 1. Okay. There's no point adding any. Just distribute the code words so that here we have 1, we have 1, here we have 1, here we have 1, here we have 1, here we have. So hence the code word is 1, 2, 3, 4, 5, 6, 7. Same as 1, 2, 3, 4, 5, 6, 7. And this is the code word corresponding to the message bit, or that's the data word. Now, the second part of the question is to derive the data word if the code word is 1, 1, 0, 0, 1, 0. When the generator matrix is given as 1 plus x cubed. Okay. Now to represent the code word again in equation form, we have c equal to 1, 1, 0, 0, 1, 0, 1. So this is x naught, x to the power of 1, x to the power of 2, x to the power of 3, x to the power of 4, x to the power of 5, x to the power of 6. So x to the power of 1 is 1, and x is on, these are off, right? Then S4 is on, is off, then S6 is on. So that's C is equal to 1 plus x plus x4 plus x to the power of 6. And g of x is the same as 1 plus x cubed. Now recall that the data word or the message bit is the same as the binary bits resulting from the division of the code word and the generator matrix. So message bit m of x or g of x in this case is the same as c of x over g of x, right? That is 1 plus x to the power of 4 plus x to the power of 6 divided by 1 plus x cubed. And now I have to do a long division. I have x to the power of 6, no s5, there's s4 plus s4, there's no s3, there's no s2, and there is x plus 1. Then we're dividing by x cubed plus x plus 1. Now, if this goes into this, x cubed divided by s cubed, that'll be s cubed here. So s cubed multiplied by this is x to the power of 6. Then x cubed times x, that's x cubed times x cubed is the same as x3 plus 3, x to the power of 6, right? So x cubed times x to the power of 1 is x3 plus 1, which is x to the power of 4. So it is plus x to the power of 4. Then s3 times this, that'll be x cubed, right? So we now have plus x cubed, and that is all. So if we subtract, this is 0, this is 0, so we have x cubed. We don't have x squared, but we have x plus 1. So x cubed can go into s cubed one time, so that is 1, yeah, plus 1. So this times 1 times this is s cubed plus x plus 1. So everything here reduces to 0, so we are done. Hence, the data word dx is the same as s cubed plus 1. So that in binary form, we now have, say, s cubed plus x squared plus x plus 1. This is turned on. This is turned on. That's to the power of 1, x to the power of 0. Then all of these are turned off. Hence, the data word d of x is equal to 1, 0, 0, 1, corresponding to that code word. Once again, on the basis of a 7 by 4 cyclic code, obtain the generator matrix corresponding to g of x equal to x cubed plus x plus 1. Hence, otherwise determine the parity check matrix. So we need to get G, we need to get the parity check matrix, and then we're also asked to get the code vector, the code word. Then we're also asked to determine the weight of the code word. Now for an NK cyclic code, we have N is equal to 7, and then K is equal to 4. Okay, but the generator polynomial is given as g of x, which is 1 plus g sub 1 x plus all the way to plus g minus r x r minus 1 plus s to the power 5. For r being the same as n minus k, which is the redundant bits. So that r is the same as 7 minus 3 and k, which is equal to 7 minus 4, that's nk. K is 4, which is equal to 3. So therefore, the generator polynomial equation has the highest power of 3. That's the implication, okay? So it has the highest power of 3. And its matrix can be formulated upon the power of 3. So hence, the highest power of the polynomial is 3. So g of x will be of the form 1 plus g1 of x plus g2 of x squared plus g3 of x cubed. Now, g of x, g of x, that's the same as g of x. Now, x squared g of x and x cubed g of x. Now have here, we have 1 plus x cubed. Here we have x plus x squared plus x to the power 4, because g of x was given as x cubed plus x plus 1, such that x times g of x will be x plus x squared, because multiplied by this. This is a polynomial, and we have the power of 3. And from this equation, we are able to generate this. Given g of x, now we can investigate, or better to get sg of x component. Then we can get x squared g of x and x cubed g of x, given g of x. So s squared g of x will be s squared times this, so that's x squared plus x cubed times s to the power 5. And x cubed times 1 is x cubed plus s to the power 4 plus x to the power 6. So for an NK cyclic code, N is the encoded block of N bits and K is the message bits. So since N is 7, the code word length will be 7. Okay, so that the N equal to 7 will correspond to g of x equal to 1 plus x squared plus x cubed plus s to the power 4 plus s to the power 5 plus s to the power 6. That's 1, 2, 3, 4, 5, 6, 7. And then by representing the above in binary format, that's this. So we have that since this is the size, this is the block length. So if we want to represent this, let's wipe the board. Then this in terms of this, we now have for g of x, 1 is turned on, x is also turned on, but x squared is not turned on, 0, x cubed is turned on, 1, then x to the power 4 to the power 6 are turned off. Now x, g of x, now 1 is turned off, x is turned on, which is 1. Now x squared is turned on, 1. X cubed is turned off, x to the power 4 is turned on, then the other two pieces are turned off. Now x squared g of x, now 1 is turned off, x is turned off, x squared is turned on, x cubed is turned on, x to the power 4 is turned off, x to the power 5 is turned on, then x to the power 6 is turned off. Now x cubed g of x, we have 1 is turned off, x is turned off, x squared is turned off, x cubed is turned on, x to the power 4 is turned on, x to the power 5 is turned off, x to the power 6 is turned on. So hence, the generator matrix G will be of the same, will be of the format G of x g of x squared g of x, and x cubed g of x, which should now be 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1. Now recall that the generator matrix is given as the parity bit and the identity matrix in a systematic code format, okay? Such that we'll have to separate the identity matrix here, but you realize that this follows, but with this bit here, we are not able to get the identity matrix having ones in the diagonal. So we'll have to perform row transformation. Okay. Now, as well as here. Okay. So if we perform row transformation, you see that G star asterisk will now give us on the third row, if we add row 1 and row 3, that modulo 2 addition, and the fourth row, row 1, row 2, and row 4, then we are going to get 1, 1, 0, 0, 0, 0. And we're going to get 0, 1, 1, 0, 1, 0, 0. And we're going to get 1, 1, 1, 0, 0, 1, 0. We are going to get 1, 0, 1, 0, 0, 0, 1. Perfect. Now you see that we have the parity matrix and we have the identity matrix. So the generator matrix G is equal to G star. Now the parity matrix, parity check matrix, is the same as the identity matrix N minus K times the transpose of the parity check matrix. So here, the parity matrix here is 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. And the transpose will be the same as 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1. Right? So in this format, so we now know we're going to get a 3 by 3 identity matrix 1, 0, 0, 0, 0, 0, 1, 0. And 0, 0, 0, 1. That's that. Then parity matrix comes in. So that's 1, 0, 1, 1, 1, 0, 0, 1, 1. And now the next thing is to investigate, is to get to generate the code words. Now recall that, don't forget this, the parity matrix. Recall that the code word B is given as the message bits times the parity, such that B1, B2, B3, which are the code words, is equal to, looking at parity 1, 1, 0, 0, 1, 1, 1, 1, 1, and 1, 0, 1. Looking at this, so it's going to be 1, 2, 3, 4. But before we conclude on this, recall that K is equal to 4. So we're going to have 4 message bits, M1, M2, M3, M4. Okay, we have a 7 by 4 NK code. So this is the message bits for message bits. So with this, we can develop the system of equations for this, such that B1 will be the same as M1 times 1 with load 2 addition, M2 times 0, load 2 addition, M3 times 1 with load 2 addition, then M4 times 1. So B2 follows directly as M1 times 1 plus M1 times 1 plus M2 rather is M2, M2 then M3 times 1, M3 times 1, plus M4 times 0, then B3 will be the same as M1 times 0 plus M2 times 1 plus M3 times 1 plus M4 times 1. So therefore, B1 is the same as M1 plus M3 plus M4, while B2 is M1 plus M2 plus M3, while B3 is M2 plus M3 plus M4. Okay, now since we have 7 by 4 NK code, now the total number of data words, total number of message bits or data word will be the same as 2 to the power of k, which is 2 to the power of 4, which is 16. Okay, so hence we have 16 distinct code words in 7 by 4 cyclic code. So to design the 16 distinct code words, we invoke the 16 possible data words using the truth table for the 16 possible binary combinations. And so we have, we have the table. So the binary, the truth table, the binary combination, the possible binary combination for the 16 possible data word will be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 2, 0, 1, 0. And now for the parity bits, can B1 same as M1 plus M3 plus M4, that is 0. And M1, M2, M3, so 0, so 0 here. And in this case, M1, M3, M4, 0 plus 0 plus 1, that's 1. Now M1, M2, M3 is 0. Now M2, M3, M4, that's 1. Now M1, M3, 1. Now M1, M2, M3 is 1. M2, M3, M4 is 1. So we're going to populate the parity bits using the system of equations. Hence we have that, and the next thing to do is to transfer all of these as the code word, and then the weight, the number of ones in this case is 0. Number of ones here, 1, 2, 3. Number of ones here, 1, 2, 3, 4. Number of ones here, 1, 2, 3. Number of ones here, 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Perfect. Why we have the distribution of. Hence, we have the overall distribution. Okay, then we can look at one more example. Say, for instance, determine the error correcting capability. Determine the error correction capability of the 7x4 cyclic code. Now, since the smallest Hamming weight for the non-zero code word is 3, the minimum distance, looking up at the Hamming weight, because now look at it, the smallest Hamming weight for the non-zero element the code word is equal to 3. Now, if we go back, we see that the smallest Hamming weight here is 3. Yeah, 3. So if we had a Hamming weight of 2, that would have been the smallest. We can't use 0 because we're looking at non-zero elements, okay? So this is 4, 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 this is 7. So the smallest Hamming weight is 3. Good. So hence, since the smallest Hamming weight for the non-zero elements in the code word is 3, then the minimum distance, the mean, will be equal to 3. But error correcting capability T is given by T greater or equal to D mean minus 1 divided by 2, which is greater or equal to 3. D mean is 3 minus 1 divided by 2 is equal to 2 divided by 2, which is equal to 1. So hence, the 7x4 cyclic code can correct single error. So this brings us to syndrome decoding. Okay. And we have seen that the generator matrix is used for the generation of code words at the transmitter, which is to be transmitted over the channel. Then at the receiver, the decoding scheme uses the parity check matrix to check for possible errors and then correct for them. So for a code word C, let's say we're given a code word C, transmitted over the channel, a noisy channel at that. The received vector, say R, let's say receive vector R, So we have C going into a channel. Here's the channel. Then we receive R is the sum of the transmitted code word plus an imposed error, superimposed error, such that we have modulo 2, such that C, let us see at the output, R is the same as C plus the error. Now, since the generator matrices are used to derive the actual transmitted code word, that is, G is used in the encoding operation. So here I have the G matrix running here. Then the parity check matrix H is used for the decoding operation at the receiver. So further to this, it is required that the receiver decodes the code word from the received vector R. And to achieve this aim, the algorithm commonly used to perform the decoding operation is called error syndrome vector, or simply the error. Hence, the syndrome is therefore related to the parity check matrix, such that the syndrome is the same as the received vector, which contains the code word and the error, times the transpose of the parity check matrix. So if this is equation 1 and this is equation 2, so if we put 2 into 1, then we have S, the syndrome, to be C plus the error, H transpose, which is going to give us C, H transpose plus E, H transpose. Now, C, H transpose gives us 0 based on our previous deductions. Then the syndrome will now be 0 plus E, H transpose, such that the syndrome is the same as the error times. Hence, the parity check matrix acts on the error. Therefore, this implies that the syndrome depends only on the error pattern and not on the transmitted code word. Now, similarly, another property of the syndrome states that all error patterns that differ by a code word have the same syndrome. So that is, if the error is the same as E plus CI, that's for I taking on values from 0, 1, 2, all the way to 2 to the power of k minus 1. Then, if we multiply this expression by h of t, that is EI, H transpose rather, CI, H transpose, this will give us EHT, CI, H transpose, G plus H transpose, once again was 0. This again gives us the same thing, and it's independent on the index I. So considering these two equations, that is related by this expression. S is called the syndrome of R. S is called the syndrome of the received vector. Now, if the syndrome is 0, if the syndrome is 0, it implies that R is a code word and is assumed to be the correct code word, the correct code word. Hence, it means it has no error, meaning it was received error-free. Okay? With syndrome decoding, an NK linear block code can correct up to T errors per code word. If N and K satisfy the following bound Q plus 1 greater or equal to summation of I equal to 0 T to T and combination, right? For Q being the same as N minus K, that is 2 to the power of N minus K minus 1 should be greater or equal to sigma for I equal to 0 to T, then N factorial, N minus 1, N minus factorial, N minus I factorial. Note that a block code for which equality holds for this expression is known as the perfect code. So when equality holds, the code is a perfect code. And that the Hamming bound is necessary but not sufficient for the construction of T error correcting linear block codes. So let's look up a few examples and then we could call it a day. So let's assume we have a 7x4 block code, linear block code, and then the parity check matrix is given as 1 0 0 0 1 0 0 0 1 1 1 0 0 1 1 1 1 1 1 0 1. Now, if the received vector R is the same as 1 1 0 1 1 0 0, now determine the corresponding transmitted code word. What is the transmitted code word? So we already know that the syndrome is the same as the received code vector times transpose of the parity check matrix. So we have 1 101100 times 100101. So we have 0101110. We have 0010111. So with this, we therefore have this row times this row times this row, then times this row. So we have 1 times 1 plus 1 times 0 plus 0 times 0 plus 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 1. So hence, what we now have is 0, 1, 1. So now that we have non-zero syndrome, so it means there's an error. So what we now have to do is to compare this with the particular column in this distribution. There we see 0, 1, 1, 0, 1, 1. I will see that it tallies with this, right? So if this is equivalent to the first bit place, second bit place, third bit place, fourth bit place, and this is the fifth bit place. So hence, first, second, third, fourth, fifth. So meaning this bit is in error. So all we now need to do is that the actual transmitted code word C is 1, 1. Sorry, let's use a black. So the transmitted code word C is 1, 1, 0, 1, 1, 0, 0. Now to confirm, we could multiply with this parity matrix such that we have 1, 1, 0, 1, 1, 0, 0 times the transpose, which is 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, and the resultant effect will be 0, 0, 0, so that the syndrome is all zeros, meaning this is the correct code word. Okay. Now, let us assume we have a 6x3 systematic linear block code, which comprises of the code word I1, I2, I3, P1, P2, P3, where the 3 parity check bits are formed, where the 3 parity check bits are formed using the information bit as follows. P1 is I2 plus I3. P2 is I1 plus I2. And P3 is I1 plus I3. So in other words, we want to determine the parity check matrix. We want to determine the generator matrix. We want to determine all possible code words. They want to determine the minimum Hamming weight. We want to determine the minimum distance. We want to determine the error detecting and correcting capabilities. Now, if, for instance, if the received sequence is 1, 1, 1, 0, 1, 0, then we want to calculate the syndrome. Well, I'll just walk through this. Nothing too serious. Now, since we have this, it's a 6 by 3, 6 by 3, and K, okay? So P here is formed using this, which is P1, P2, P3, okay? And now we have NK, and then the message bit here will be 2 to the power of K, which is 2 to the power of 3, which is 8. So we can form that distribution quickly by, say, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 2. Okay. So from this, can I move forward? So from this, let's see, let's write this. Okay, let's leave it ISO 1, ISO 2, ISO 3. Now to populate this, we have I2 and I3 are turned on. So if this is I1, I2, I3, so it means I2, I3 are turned on for P1, so that is 1, 1. So this is 0. For P2, I1 and I2 are turned on. This is 0. For P3, I1 and I3 are turned on. And this is 0. So we have this. Now, recall that the parity matrix is IN is K, P transpose. So we take the transpose of this such that the transpose will be 0, 1, 1, 1, 1, 0, 1, 0, 1, such that the H parity check matrix now will be 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the identity matrix, and 0, 1, 1, 1, 1, 0, 1, 0, 1. So we have that. So the generator matrix follows directly from here, G, which is P. Okay. And we already have the parity matrix, so that will be 0, 1, 1, 1, 1, 0, 1, 0, 1. That will be 10000100001. And since we already know this, then the parity bits can be evaluated from this. So P1, P2, P3, right? So we already have the models, 3, 2, that's 2, 3, 0 here, so zeros. Then here for P1, 2, 3, that's 1, 2 plus 3. Then for P2, 1, 2, that's 0. Then for P3 is 1, 3, 1, 3, that is 1. And here again, for P1 is I2, I3, I2, I3, that's 1. For P2, I1, I2, that is 1. For P3, I1, I3, I1, I3, that is 0. So here we have 0, 1, 1. Here we have 0, 1, 1. Here we have 1, 1, 0. Here we have 1, 0, 1. Here we have 0, 0, 0. Perfect. And then the minimum weight, or better say the minimum Hamming weight. So here we can calculate the weight, WC. This is 0, this is 3, this is 3, this is 4, this is 3, 1, 2, 3, 4, this is 4, 2, 3, 4, then 3. The minimum Hamming weight, minimum Hamming weight, minimum Hamming weight is equal to 3. And as such, the minimum distance, d min, is also equal to 3. Now the error correcting capability is still greater than or equal to d min minus 1 over 2, which is greater or equal to 3 minus 1 over 2, which is greater or equal to 2 over 2, which is equal to 1. So t is greater or equal to 1. So the code is a single error correcting code or double error detecting if no correction is required. Okay, and now the syndrome is we still have some space. Okay, syndrome is s equal to r rht such that the transpose, which is the received word here, is 1, 1, 1, 0, 1, 0. So I'm going to multiply by the transpose of the H of the parity check matrix. So that's 1, 0, 0, 0, 1, 1. Then we have 0, 1, 0, 1, 0, then 0, 0, 1, 1, 0, 1. And once you multiply through, so we're going to get 0, 0, 1. So there's error somewhere here. That's on the 1, 2, 3, 4th bit. So hence, the transmitted code word is the 4th bit should be 1, 1, 1, 1, 1, 0. Okay. Good. And then that's that. So let us consider a final example. Then that will be it. So let's say for linear block code n minus k, which corrects single error per code vector, show that n is greater or equal to k plus log to base 2 n plus 1. So, well, from this, we recall the Hamming bound given by 2 to the power of q minus 1 greater or equal to 0 t n combination I for q being the same as n minus k, so that 2 to the power of n minus k minus 1 is greater or equal to summation of I equal to 0 t n combination I. Now, since the nk linear block code corrects single error per code vector, we have t equal to 1. Therefore, 2 to the power of q, or better still, let's just go by the nk. So already expanded that. The power of n minus k minus 1 is greater or equal to n combination 1. So 2 to the power of n minus k minus 1 is greater or equal to n factorial over n minus 1 factorial and 1 factorial, right? So what we now have here is n times n minus 1 factorial over n minus 1 factorial. So this will cross this. So 2 to the power of n minus k minus 1 is greater or equal to n. So that 2 n minus k is greater or equal to n plus 1. So taking log to base 2 of both sides, as we have log 2n minus k base 2 greater or equal to base 2 n plus 1. This now gives us n minus k log 2 base 2 greater or equal to log 2 n plus 1. So this reduces to 1. So n minus k is greater or equal to log n plus 1 base 2. So then n is greater or equal to k plus log n plus 1 base 2. And I think this is a good place to stop, and hope to see you in our next class. Bye for now.